This is joint work with Nima, Labchi, and Cheyenne. So I'm going to start with talking about graph decompositions. The basic idea is we have a graph, and all the graph I'll be using in this graph, or I'll be talking about in this talk, will be unweighted deregular. You can extend everything to weighted graph, but let's keep things simple. So I'm given a graph, unweighted deregular, and I want to delete a small number of edges from this graph to have the graph decompose into components satisfying nice properties. So these nice properties can be things like low tree width, low shortest path diameter, or high expansion. So basically properties that allow me to solve hard problems easier than in the general case. And I want to exploit this. So in this talk, I'm going to be adding to this list the decomposition into low effective resistance diameter components. But before I do that, let me talk about low diameter graph decomposition and expander decomposition, since they are conceptually relevant for my talk. So in low diameter graph decomposition, I'm given a graph and a parameter delta, and what I want to do is I want to cut the graph into pieces such that each piece has a shortest path diameter at most delta, and there aren't too many edges in between the components. So like the smaller delta gets, the more edges I'm going to have to cut, but I want the fraction of the edges I'm cutting to be scaling like 1 over delta, and I'm going to quantify how far away from that case by a parameter called the distortion. So I'm going to say that the actual fraction of the edges that I'm cutting is d of g over delta. And I want this d of g to be order 1. And indeed, when it's order 1, this technique is very useful. I get very cool approximation algorithms for fixed minor free graphs or bounded genus graphs. But for graphs as natural as the hypercube, this isn't the case. So if you have a hypercube, this parameter scales like log n, which means if you want to cut at most a constant fraction of the edges, you have to settle for a diameter of omega log n. And for many applications, this simply is not good enough. Similar idea, expander decomposition. This time you're given a parameter phi. You want to cut the graph into pieces such that each component has expansion at least phi. And you want that the number of edges you're losing is small. And of course, like the larger phi is, the more edges you're going to be forced to cut. But I want the fraction of the edges I'm cutting to scale nicely. So I'm going to say f of phi for some nice mild function of f. Of phi. And again, very useful technique. But thing is, for a graph as natural as the hypercube, if you just fix phi, you're going to see that if you want to have or rather, if you want to have components of expansion phi, this fraction is going to scale with log n. So it depends on the graph size. So if you want to cut a constant fraction of the edges, you can only guarantee an expansion of inverse d log. And again, for many applications, that's not good enough. So what we say at this point is maybe we don't have this, or maybe we're suffering this log n loss, because the properties we want are too strong. Also important to note is that the cases where I can decompose into low shortest path diameter graphs are kind of the opposite case of the expander graphs. So like graphs like fixed minor free graphs or bounded genus graphs. So I'm saying, okay, maybe there's something in the middle. Maybe there's a weaker property that generalizes both. Maybe there's a weaker property that both of these properties share. And maybe I can decompose into that property without losing that log n. And what we considered in our paper is the property of low effective resistance diameter. I'm going to define what that is. But for now, let's just assume that it's some abstract distance metric on a graph that generalizes both the low shortest path diameter and high expansion. So for shortest path diameter, this is a folklore result. It's very well known. And for high expansion, it is due to the work of Chandra and friends. So they show something more general, actually. They show that if you have a deregular graph, its resistance diameter is ordered 1 over d, and this is best possible. That is, if you have any deregular graph, you can hope for better effective resistance than 1 over d. Okay, so what we show is that we can decompose into low effective resistance diameter partitions. So if you give me a deregular unweighted graph and some parameter delta larger than 1, I can cut a 1 over delta fraction of the edges and get that the effective resistance of every cluster is at most delta cube over d. The interesting regime for me is where delta is some constant, say 100. So what I'm doing is I'm cutting less than 1% of the edges, and getting that effective resistance diameter is order 1 over d. So again, like this is asymptotically optimal. So what you're seeing here is that we cannot decompose into low diameter components or expanders, but we can capture their electrical properties, which is kind of cool. The complexity, I don't know whether I'm going to explain, but the basic idea how we compute this decomposition is we show that if you have vertices in a graph which are well separated from each other in the effective resistance distance, then you can find a very sparse cut separating them. So the sparsity of the cut is essentially like 1 over square root of the size of the set, side of the like small side of this cut. And if you just keep along those cuts, you can get the decomposition from before. And finding those cuts is very simple, it turns out. You can do that just by solving a Laplacian system. OK, so now let's make this concept of electrical flow and effective resistance a little more concrete. So the basic idea is you have a graph, again animated, and now you're interpreting this graph as an electrical circuit. So you're saying, OK, my every edge is a unit resistor, and I'm hooking up a battery to S&T, and I'm sending 1 unit of, or like 1 ampere of electric current through the graph. I'm going to have some sort of flow. Physics tell me that I'm going to get some sort of electricity there. And that will be the object that I'm studying. So I know that this is going to be a flow in combinatorial sense, in that it's going to satisfy flow conservation. And it's going to satisfy this additional property called Ohm's law, in that it's going to be a potential flow. So the flow, for me, is just going to equal to the potential difference between the edges. So this might be a little strange, but this is essentially what's happening. You have one vertex V. You have 0.7 units of flow coming into that vertex. All 0.7 units of that flow leaves that vertex. And then you see that the flow between V and neighboring vertices is just defined by the potential difference. So 2 things to note. 1, the flow is just the potential difference. 2nd, the flow flows in the direction of the potential drop. So if you have an edge, the flow in that edge flows from the higher potential vertex to the lower potential vertex. So this will be important. Let's take a second and digest this. Good. So the idea of effective resistance just is just we're carrying this analogy further. So we have a circuit, and now we're saying, OK, this entire graph is just a resistor between the vertices S and T. And by rearranging Ohm's law, I can just say that resistance is just a ratio of potential difference and flow. So I'm routing 1 unit of electric flow from S to T, and I'm measuring the potential difference, and I'm calling that the effective resistance. Again, like this is just the resistance of the graph between S and T. I'm just interpreting the entire graph as a very big resistor. And the intuition we have here is that the more an ST flow can spread out, the smaller is the effective resistance. And by spreading out, I just mean it's uniformly small over the edges. So like so almost every edge sends a very small flow. So for a path, this is not the case. Every edge has large flow. So for the endpoints of a path, I have very large effective resistance. For parallel paths, I can spread out comparably nicer. So the effective resistance part you get is relatively better. For a deregular expander, again, as I mentioned before, the effective resistance is order 1 over d for every pair of vertices. And then we have the curious case of the d-dimensional mesh. And by the way, for the expander, this is more or less what you would expect, because in an expander, you have many paths. So you can spread out fairly easily. But for the curious case of the d-dimensional mesh, which is a very bad expander, if d is larger than 2, you have the same electrical property as the expander, in that the flow can spread out very easily. But then you have this phase transition at 2, which prohibits the flow from spreading out easily. So you have the resistance bound of log n. So these 2 results are from the same paper, but they use different techniques. And what we're going to do is more or less going to unify those 2. OK? And before I want to move on, I just want to emphasize that this effective resistance parameter is not just a parameter that I made up. It has many probabilistic interpretation in random walks. And those probabilistic interpretations make it very useful in algorithm design, like countless applications. So I'm just going to talk about how to find the sparse cut now. But I'm going to prove that in the contrapositive. So what I told you before is that if there's a pair of vertices in my graph, which is well separated, I can find a very sparse cut. And now I'm going to prove the contrapositive in that I'm going to say if every set I have expands just a little, the effective resistance between every pair of vertices will be very small. So this looks a little hostile, but this epsilon term I have, wait, does it work? Yeah, this epsilon term I have is essentially going to quantify how far I am from the case of the expander and how close I am to the case of the two-dimensional mesh. So if epsilon is 1/2, this is just going to die out. So you're just going to have the definition of the expander. And here, this term is just going to be 1/d. And if you're an expander, this is omega-1. So you're just going to reprove the result about the effective resistance diameter of the d-regular expander. And if epsilon is tending to 0, let's take it 1/log n. And if you see some constant again, you're going to get the result about the two-dimensional mesh. So you're really interpolating between these two cases. And if you pick epsilon like something like 1/6, you're going to get the case of you're more or less going to get the case of the three-dimensional mesh. OK, so what we're saying is that we are requesting every set to have expansion slightly better than inversely square root of the volume. And then we're going to show if that is the case, then the effective resistance diameter of the graph is bounded. And the way we do this is by looking at the potential sets of the threshold sets of the potential vector. And my idea of showing this is essentially going to be ball growing. So I'm going to start with the potential set just containing the vertex S. And I'm just going to gradually expand that until I cover half of the vertices. Then I'm going to do that from T. In the end, I'm going to show that more than half of the vertices have small potential difference to S, and more than half of the vertices have small potential difference to T. So there should be some vertex in the middle, which is very close to both. And that's going to essentially prove the statement that S and T have a very small potential difference. OK? And again, we're going to assume that the same thing from here, that all these sets are mildly expanding, in that their expansion is slightly better than inverse square root. And essentially, these sets are some objects that I can browse through just by solving a Laplacian system. So this is where the algorithmic side of the result comes from. OK, the idea is actually very simple. Our intuition is that if you have a threshold cut like this, then because every vertex in S theta has higher potential than every vertex in S theta complement, the electric flow flows from inside S theta to outside S theta. So the total flow crossing the cut is 1. So flow does not remain trapped in the set. And further, or rather, you don't have many back and forth things in between the sets. And second thing is the mild expansion property implies that there are many edges crossing the cut. And again, total flow in my case is just a potential difference. So what I can say is that the average potential drop is small. So there are this many edges. So the average is just 1 over the size of the cut. And then by using Markov's inequality, I just say for many edges in the cut, the potential drop between the endpoints is very small. So the potential drop, or rather the potential difference between the endpoints and theta is going to be very small. So like order 1 over size of the cut. And if I just drop the potential by a little, I can introduce many new vertices. This is just the basic idea. Let's make this more formal. So I have the set S theta, and what I'm going to do is I'm going to find the set F, which contains a significant chunk of the cut. And this is going to have like all the endpoints of the set F which don't lie in the set S theta are going to have small potential difference with theta, because this is what I just assumed here. And I'm just going to extend the set S theta by those endpoints. And because my graph is deregular, I'm going to have many unique endpoints here. And I can just use this to show that if I drop the potential from theta to theta minus order 1 over size of the cut, I'm going to add this many points, like size of the cut over d many endpoints. And here, what I do is I just repeat dropping the potential by this amount until this term becomes S theta. And what that gives me is this inequality, in that if I just drop the potential, yeah, this is misaligned, but whatever. If I just drop the potential from theta to theta minus d size of the set over the size of the cut squared, I'm going to double the size of the set. And what I'm doing here is that I'm assuming this mild expansion condition. And that's going to show me that the larger the set is, the smaller is the amount I have to drop the potential to double the volume. So this is a little hard to read, I guess, but what I'm going to do is I'm going to start with the potential set which just contains the vertex S. And I'm going to drop the volume to double the set. I'm going to drop the volume to double the set. I'm going to drop the volume to double the set. I'm going to drop the volume to double the set. And eventually, I'll cover more than half of the vertices. And the potential drop I have to make is just this thing, I guess flipped. But the thing is that it depends geometrically on the size of the potential set. And if I'm dropping it, so if I'm doubling the size of the set every time, then these potential drops are going to form a geometric sequence. So I can say, if I just solve this geometric sequence, that between the zeroth set and the kth set, there is going to be this many, or there's going to be this many potential difference. And the set fk will contain, if I just repeat this more than log n times, or like order log n times, I'm going to cover more than half of the set. So if I do this from S, I'm just going to get this statement. If I do this from T, I'm going to get the symmetric statement that from T to half of the vertices, there's a very small potential difference. And then I'm going to unify those both statements to get the result I have. Okay? And if you just apply this naively, you get something worse than the bond we have. But I think this is still mildly interesting. So I'm just going to talk about this because it allows me to override some technical issues there is in the version of the paper. So I'm just going to cut the graph along the sparse. So I'm going to set a potential target R. And so long as my graph contains two vertices, which are further from each other from R, there's guaranteed to be a sparse cut. And I'm going to cut the graph along that cut and recurse so long as every component I have is of diameter R. And again, sparse for me means the expansion is approximately like inverse square root of the size of the set. And the way I analyze the number of the edges I have, how many minutes do I have left, by the way? 2, 3? Okay. And the way I analyze this is essentially by some sort of amortization. So what I'm going to do is I split these both sets. And the edges that I'm losing, I'm going to charge the small side of the cut. So the edges on the small side of the cut will pay for the number of edges I'm losing. And essentially, from this assumption, I'm going to build a geometric series to conclude that an edge is not going to be charged too many times. I guess I'm satisfied with that explanation. So I'm just going to move to the conclusion and open question. So again, we showed that if you have a pair of vertices with high effective resistance, you can find very sparse cuts. It is possible to decompose a graph into low effective resistance diameter pieces without losing too many edges. These are the two results we have. And I guess the low-hanging apple right now is the question whether this decomposition is useful at all, because we don't know any applications, but it would be cool to have applications. And another easy question from this point is whether we can k-partition a graph, which is like better than applying the same lemma order k times.